we're all here.
I'm here.
Good afternoon, everybody. In our job as metrologists, we are required to make incredibly accurate measurements, and as time goes on, we find standards that are more and more accurate. One of the tenets of being in PMIL and being a metrologist is to have traceability. What we do is we'll have our base measurement standards, which go higher and higher up to NIST standards, all the way up to like the primary standards that the entire world uses. In 1960, the international community decided that we're not able to really use the physical standards that we have anymore, and we need to come up with a better way of getting more and more accurate measurements. Of the 7 basic units of measurement, there's only one left that's still a physical measurement standard, which is the kilogram. And today I'm going to tell you a little bit about the history of the kilogram, how it's created, the kilogram standard we use currently today, and then the future of the kilogram and the way it's going to be a fundamental constant of nature. Towards the end of the 1700s, King Louis XVI was having a pretty hard time with commerce and trade. There was no set standard on how much something should weigh. So if you have a bag of wheat you're trying to sell at a trader, they might give you 14 pieces of gold or something like that, and then you go down to the next trader and he'll only give you 9 because their scales weren't calibrated at the same measurement standard. So they came up with a commission that was create a standardized way of having weights. And the way they used it was called the grave. And the grave was 1 liter of water at its ice point. How much that weighed was the unit of measurement, and they calibrated all their scales that way. Once the French Revolution happened, the metric system was created, and they changed the grave to the gram. And the gram was 1 cubic centimeter of water at its most densest point, which is at 4 degrees Celsius. Unfortunately, that's a kind of an impractical way of measuring something because 1 cubic centimeter of water is about the size of a pea. So they came up with something that was 1,000 times larger, so it was 1,000 cubic centimeters of water at 4 degrees Celsius, which was the kilogram. Which brings me to my second point, which is what the standard we have nowadays. So in 1875, the Federal Bureau of International Weights and Measures in France, they came up with the International Prototype Kilogram. And so it's made of 90% platinum and 10% iridium, and it is the exact weight of 1,000 cubic centimeters of water at 4 degrees Celsius. This thing is kept inside of a triple sealed airtight container, and what they do is roughly in 1875 all the world powers came together and they wanted to come up with a way of having trade and commerce that was pretty effective and efficient, and so they all agreed to use the metric system. And so once all the countries signed saying we're going to use the metric system, they made 40 copies of this kilogram weight by PK. And I sent them out to all the countries who signed for that. According to this article called Redefining the Kilogram in January 2017, the US has 2 of these IPKs. That's called K4 and K20, so it's the 4th one made and the 20th one made. And they use it as a national kilogram standard as well as the Czech standard. Unfortunately, because it's a physical item, it decays over time, even if it's a metal, and so it loses micrograms of weight every single year. And Dr. Stuart Davison of the National Physical Laboratory said to Wired Magazine, while we can live with a few microgram changes over a few years, what we're looking for is something that's going to be fundamentally constant forever. That brings me to my last point, which is the future of the kilogram. After World War II, the scientific community had blossomed into like dark ages of barely having an airplane to making nuclear bombs. And so as we need more and more accurate measurements and we're getting ready to go into space, the physical standards we had were just not going to cut it anymore. So in 1960, the International Community for Weights and Measures got together, and so they're going to redefine all the basic units of measurement into something that's a fundamental constant of nature. And the first one they changed was the length of the meter. So it used to be a meter was an actual bar that was a meter long. They changed that to how long it took light to travel from one point to another. They knew the speed of light, so they can say that if it travels for this amount of time, it travels the equivalent of 1 meter. And the speed of light in a vacuum is always going to be the speed of light, so it's a fundamental constant, never changing. And so they went through and changed the other 6, but the last one they have is the kilogram. So they're trying to figure out a way to accurately measure a kilogram using some sort of fundamental constant. In 1900, Max Planck discovered Planck's constant, which describes photon energy at the quantum level. And one of the things they can do is you can figure out the energy released with mass. You can use electricity to come up with a constant for that. And so NIST came up with a thing called a Watt balance, which looks like that. And a Watt balance, what is this? It's an electromagnetic balance, basically. What they'll do is They have a test bed in there, and if they start pumping current in there, they can be able to balance the weight. And if they understand what Planck's constant value is, they can multiply it by a certain amount, and that'll cause the balance to be floating, kind of almost like a what's it called? Supermagnetic forces. And so what they do is, in 2016, Physics World said that NIST was able to measure Planck's constant within 34 parts per billion, which is pretty phenomenal for measure accuracy. And so with this new definition of the kilogram, it's supposed to be released in 2018. We're trying to get down to 20 parts per billion. So right now there's 7 countries who have watt balances, and they're all competing to see if we can get down to 20 parts per billion the fastest. And so once we're able to pull that off, then we can officially redefine the Planck's constant as, or redefine the kilogram as a measure of Planck's constant. In summary, I went over the creation of the kilogram back in the 1700s to the actual international prototype kilogram was built in 1875, and we use all the way up until today. And then the future of the kilogram, which is starting hopefully in 2018 as a value of Planck's constant. With all these new measurements now defining as constants, there's pretty much a whole new world of measurement that we can do. It'd be finally nice to get rid of a piece of platinum that we've been using for the last 150 years to measure the kilogram. Thank you for your time. And have a wonderful day.